These next two problems are going to be doing inverse trig functions. We have these problems that kind of have denominators that have not so much these, but more so this look to them. But they're a little more challenging because there's quite a bit extra stuff you got to do to it. So part of the first thing is recognizing that it's not just a pure u substitution, because if I do the derivative of this, derivative of x squared, I do get an x, but I don't know where the 5 is going to come from. And so it's not quite just this nice u substitution and then just do my stuff. So my other option is, hey, I recognize that looks like a denominator that I'm familiar with. And so it looks like it's going to be this type of a problem. But I got to set it up to make that work. And so here's how we end up doing this one. We're going to break this into two pieces. We're going to break up this numerator with this common denominator. So we're going to have a 6x over x squared plus 1 dx, and then plus, I need a little space for some work, 5 over the x squared plus 1 dx. So I'm breaking up my fraction into two fractions with common denominators so that I can add it back together if I wanted to. But I'm breaking it up on purpose. So this one, because I don't have that 5 on there, I can just do a u substitution out of this and go, I'm going to let my denominator be my u, so x squared plus 1, and I do my du, which is going to be 2x dx. Right? I'm going to get that 2 out of there, so 1/2 du equals x dx. So here's what I'm doing. I'm going to rewrite this to basically show that I can create that perfect x dx out of this fraction. So if I do that, I can pull the 6 off. I can pull the x off of the fraction and make it a 1 over x squared plus 1 x dx. So there's my x dx, which means I can replace it with a 1/2 du. The 1/2 I'm going to put on the outside, and the du I'm going to put on the inside. So I'm going to have 1/2 of 6. And then I also have a u substitution with my x squared and my du. Right, so let me finish this one. This is going to be a 3, and then my antiderivative of 1 over x is the natural log. So this is 3 natural log absolute value of u, which is going to become 3 natural log the absolute value back of my x squared plus 1. All right, so then I got to work this one. So I'll be tacking on more onto this once I kind of work through this one. So let me cut this off here a little bit. Now this is actually going to be a little bit nicer. This one almost perfectly has that look to it if I could just pull the 5 off of it. Right, my perfect square is just a 1, and I just perfectly have x squareds in there. So I'm going to have an inverse tangent, and my a value is going to be a 1, so I'm going to have a 1 over 1 and an x over 1. So let me rewrite one time on this one to kind of get this thing ready to go. So I'm going to pull the 5 off, and then now I have 1 over x squared plus 1 dx. And if I want to, I can write this as 1 squared. That's my a value. And so when I rewrite this, I'm looking at having 5. And then I would have that value is a 1, so it'd be a 1 over 1 and an x over 1. So no reason to write the over 1s. I'm looking at 5 inverse tangent of x. So then I can tack that back onto my other part, plus 5 inverse tangent of x plus c. So that one's definitely a tricky one because you got to break up and recognize that you have an inverse tangent kind of flowing into this, but not necessarily on everything. So it ends up being a mix of things. And then this one is also has something, because if you do the derivative of this 4x squared, you're not getting the top. And so right away, it's like, well, I can't do that, but it still has this inverse trig, inverse tangent feel to it, right? So I have to do a little bit of work on that one. So I have to manipulate this very different. So I'm going to take this denominator and I'm actually going to divide it into this piece to see what we have. Right? So if I'm going to do that, I need to do long division. So 4x squared plus 0x plus 1 is going to divide into negative 8x cubed plus 8x squared minus 2x plus 3. All right. So lovely long division. So I'm trying to figure out what am I multiplying 4x squared by to get negative 8x cubed. And I'm going to be 3 terms down. So I'm going to multiply that by negative 2x. Just fix that, clean that up. Negative 2x. All right, so I'm going to multiply this by negative 2x. So it'll give me a negative 8x cubed plus 0x squared minus 2x. And if you remember with division, we're then going to subtract all those pieces, which changes all of their signs, and then combine. What should happen is I set it up for those to go away. This, whatever happens after it, happens after it. So this is an 8x squared plus 0x plus 3. So I got to do one more. I'm going to multiply that by 2 to get 8x squared. So plus 2. So that's going to get me an 8x squared plus 0x plus 2. And then I will be subtracting, so I'll switch their signs. That goes away like it should, and I have a remainder of 1. So what that means is I can rewrite this problem as negative 2x plus 2 plus 1 over 4x squared plus 1 dx. So that's an equivalent form of that. So I write that because I can do my antiderivative of this, and this now has a perfect actual feel for that. So, but this one's a little bit trickier because it's not as straightforward. I can do these no problem. This is going to be a negative 2x. I add my power, divide by my power, plus a 2x. So I'm just looking at a negative x squared plus 2x, and then whatever that is. So the whatever that is let me work through that piece. So I'm going to be doing the integral of 1 over 4x squared. Right away, I'm going to write this not as 4x squared because the formula wants a piece squared plus 1 squared. Right, so I need that look to it. So I have a u substitution. I'll let my u equal to 2x. My du equals 2dx. Sorry, squeezing that in. And then bump the 2 over. So it's a 1/2 du equals dx. So got to rewrite to perfectly line up with that formula. 1 over u squared plus 1 du. And I have a half that I'm going to bring to the front. So antiderivative of that is perfectly this formula with 1s on the a's. So it's just inverse tangent of u. So 1/2 inverse tangent of u. Then I'll sub back in my 2x to finish this off. So plus 1/2 inverse tangent of 2x plus c. So that one's even more tricky because we recognize that we have this inverse tangent field to it, but the top is a disaster. So we have to do long division to write it into a different equivalent form. And that's that extra piece that perfectly kind of works into the inverse tangent. All right, so that was 2, definitely rougher inverse tangent involving trig.